All right, so in section 10.6, we're going to be looking at one of the applications of derivatives, and that is called differentials. To start differentials, we need to look at increments. So first, let's draw the standard picture here for increments, and that is we're on huge here. So suppose we have this picture. I can draw a better picture than that. So suppose we have this graph here, and we have a point here with x, and we have a point here. Let's call this x1, and let's call this one x2. Now, this is the function f. So the y-coordinate at this point is f of x1. So you take the x and you plug it into the function f. And let me extend the y-axis here. So this point has a y-coordinate of f of x2. What we are looking at today is the increments. And the increments are how the different variables change from one position to another. So if I look at the change from x1 over here to x2, we are going to call that delta x. The triangle is the Greek letter capital delta, right? It's basically our D, and it stands for change. So given y is equal to the function f of x, delta x is x2 minus x1. It's not quite distance because delta x could be negative. All right, and distance is not considered to be negative. So if the x2 happens to be on the left side, then we would have a negative result here. And this is just the change from x1 to x2. Next, we want to look at the change in the y position. So here is the current value of the first point, and the y value is f of x1, and that is going to rise to this y value, which is f of x2. So this piece right here is delta y. And so delta y is the change in the y's. So you can think of it as y2 minus y1. Using the notation we already have on the board, that's f of x2 minus f of x1. There's one more way to symbolize this, and that is to consider x2 to be x1 plus delta x. So if x2 is x1 plus delta x, then I can replace the x2 in this formulation with f of x1 plus delta x plus, minus f of x1. Well, what is that starting to look like? That's the numerator of the difference quotient. And playing the role of h today will be delta x. But that's what the h was always intended to represent. It was the distance from one point to another, and in order to get the slope of the tangent line, we took that distance down to 0. All right, so those are some of your basic working formulas. Here's the one for delta x. Here's the one for delta y, and these are called increments. Example 1. Let f of x equal x squared. For x1 equal to 5 and x2 equal to 6, compute delta x, delta y, and then delta y over delta x. So let's start with delta x. Delta x is equal to x2 minus x1. x2 is 6. x1 is 5, so the increment for x is 1. And that just represents you moving from one point to another point by moving over 1 unit to the right. Delta y is f of x2 minus f of x1. So this would be f of 6 minus f of 5. The function is the square function. So we're going to take 6 and we're going to square it. Minus, we take 5 and we square it. So we get 36 minus 25, and that is 11. So the increment for y from the points where x1 is 5 and x2 is 6, the increment for the y is 11. We're going up by 11. Lastly, we want to compute delta y over delta x. And we just use these numbers. This would be 11 over 1, which is 11. Why do you think this problem asks for delta y over delta x? What does that represent? That is slope, yeah. And in this case, because the 2 points are separated, it's a secant slope. If you'd like to draw the picture that goes with this, it looks something like this. You have the parabola, like so. And then you have where x1 is 5. Are they trying to get in? No, okay. Let me put a 5 down here. And of course that's 25. Because it's on the square function. And then here's 6. And that's 36. So delta x here is 1. And, right, so that's a 1. And the vertical change is 11. The ratio delta y over delta x is the slope that goes through those 2 points. And maybe if I draw it this way, it will make more sense to you. Here's 11 and 1. You remember one of these things you learned in high school algebra was about how to represent the slopes. What's the phrasing? Rise over run, right? You remember this? Well, that's all you're doing. The rise is delta y. It's the increment for y. The run is delta x. So you're rising and then you're running, and so that gives you the slope. Questions? Okay, page 2. All right, one of the applications of increments is to find what we call the differential. So recall the formula for derivative. The formula for derivative, the long way, is the limit as h goes to 0 of f of x plus h minus f of x over h. And as previously mentioned, instead of h, let's use the increment, delta x, and reformulate this formula. So this would be f prime of x is equal to the limit as h goes to 0 of f of x plus delta x minus f of x over delta x. And I said h here, that actually should be, of course, delta x. right there in the limit. Now, what is this numerator part? F of x plus delta x minus f of x. What is that in terms of increments? That's delta y. Yeah. So this is really, the limit is delta x goes to 0 of delta y over delta x. Because this numerator part is just the increment of y. Now, we need a little bit of theory here. You know that when you take this limit as delta x goes to 0, delta y over delta x is going to equal f prime of x. What happens right before we take that limit? You know, the limit is with the delta x going to 0. Well, what happens if the delta x is just really small? Then it's true that the values you get from delta y and over delta x, they're not going to be exactly equal to the derivative, but because the limit works, we know that these values are going to be very close. Okay? So in other words, we know that this should be equal to the derivative when we take the limit, and when the delta x is getting closer to 0, these values are going to approximate the value of the derivative at that point. The limit just, the derivative can't just sort of sneak up on you, in other words, right? The limit forces everything to move smoothly into place. You can't have some values that are just way off from the derivative and then suddenly, boom, there's the right answer for the derivative. It can't work that way. The limit has to be a very smooth function, very smooth process. So what we say here is for small values of delta x that are not equal to 0, let's put that in parentheses, that's important, then we know that the derivative is approximately delta y over delta x. So we have this approximation for the derivative. From this approximate equation, I can get the following. I'm going to cross multiply by delta x, and I'm going to solve for delta y. So delta y, I'm writing this on the left now, but this is delta y. The delta x is going to cross multiply to this other side. So delta y is equal to f prime of x times delta x. And I shouldn't say equals, I guess. I'll say approximately equal. Say approximate. The equality comes in what we call the differential. We're basically going to replace these deltas with a new symbol, that is just dy, and claim that that is equal to f prime of x times dx. And the dy is the differential of y, the dx is the differential of x. The normal assumption here is to do the following. We use this equation to approximate delta y by finding the differential of y, dy. With the assumption that delta x is equal to the differential of x. So if it says find the differential or use differentials, that's the equation they want. So in other words, we're going to be looking for the changes in y without directly finding the change in y. Instead, we're going to use calculus, and we're going to approximate those changes through this differential. So let's work our way up to that. Let's do some examples to show us how this works. Example 2, find dy, the differential of y, for the equation y equals 8x squared plus 4x minus 2. So the formula for the differential of y is f prime of x times dx, the differential of x. So this is dy is equal to, now we look at the equation. What is the derivative of this equation? Yeah, 16x plus 4 times dx. And that's it. So we formed the differential of y by taking the derivative of the function and then literally multiplying it by the differential of x. We will use the dx in applications, but here it's notational. Okay. Let me show you how good of an approximation this stuff actually is. Let's look at example 3. Suppose you have this function, f of x is equal to x squared plus 3x plus 9, and you want to evaluate delta y and dy given the base number of x equals 3 with delta x equal to 0.1. So again, this is the delta x has to be small for this stuff to make any sense. Let's do the delta y first. Now remember, delta y is an exact difference. So this is finding the exact difference. So delta y is equal to f of x plus delta x minus f of x. So the x represents a starting point. The delta x represents how far over to the right or left if it's negative. But in this case it's positive, so it's right of the point that you're considering. What is the x in this case? 3. And what is delta x? 0.1 minus f of 3. The function is here. And so this is asking for f of 3.1 minus f of 3. I've worked this out for us ahead of time. F of 3.1 is 27.91, and then f of 3 is 27, giving us a difference of 0.91. That is the exact change from 3 to 3.1 on the y values. Next, we want to find the approximate change. The approximate change is the dy, the differential of y. So the first thing we will do is we will find dy is equal to f prime of x times dx. The derivative of x squared plus 3x plus 9 is 2x plus 3. And now we need to use the value of x where we are located. So this is x equals 3. And then for the dx, remember that we use differentials under the assumption that the dx is equal to the delta x. So the delta x here is 0.1. Two times 3 is 6, plus 3 is 9. So this is 9 times 0.1. 9 times 0.1 is 0.9. Notice how close the approximate and the exact numbers are. Example 4, estimate the shaded area shown below. The radius of the circle has been increased from 6 centimeters to 6.25 centimeters. So to do the estimate, we'll use differentials. So first we need an equation. We're looking at area. So the area of a circle is pi r squared. Oh, it's not on the screen. Sorry. It's pi r squared. And if you want to use x's, you can use an x. It doesn't matter. You can use an x for the radius. So pi x squared. What is the delta x? What is the change in the radius? 0.25 centimeters. All right, now let's look at the differential. So it's dA is equal to a prime of x times dx. Substituting all the right variables here, right? The function is an a function, so on the left it's dA, and then it's a prime of x as the derivative, and then times dx. What is the derivative of a equal to pi x squared? And I'll give you a little hint on how to figure this out. Pi is just a constant, so just ignore it and then multiply by it at the end. What's the derivative of x squared? 2x. So this is 2x times pi. The pi is still there. And then times dx. And now, just as before, there's some sense of you starting at a position and moving to another position. Here we started where x is equal to 6, and then it went to 6.25. So the x is 6, and then dx is the same as the delta x. So it's 0.25. And then if you figure that up, it's 3 pi. What are the units on this, by the way? 6 here was centimeters. 0.25 was centimeters. So this should be centimeters squared. Does centimeters squared make sense for the units for this? What does dA represent? What does it mean in words? And what's that? No? Area. Area. So this is the difference in area. What units are appropriate for area? Square units. Centimeters squared. All right. Next page. Example 5, approximate the value of the square root of 102 using differentials and without using a calculator. So, first we want to figure out what function is involved in this problem. So what are we doing to the 102? Square root. So that means the function is the square root function. Now, in order to do this without a calculator, we're going to need to know something for certain. Based on the previous graph that I showed you, you know that you need to know information that is close to the one that you actually want. You actually want the square root of 102. So do you know any perfect squares that are close to 102? 100. So that is your fixed x point. X is 100. What is your delta x? 2. Yeah. So you're starting at 100 and you're moving up to 102. All right, so here we go. What is the derivative of the square root function? 1 over 2 root x. Now we'll use the differential. So dy is equal to f prime of x times dx. This is 1 over 2 square roots of x times dx. Plug in your fixed value for x, which is 100. And then assume that the dx is the same as the delta x, and that's 2. The 2's cancel. The square root of 100 is 10. This is 1/10, which we'll write as 0.1. So that is the approximate change in y. That's not the answer, right? The square root of 102 is not 0.1. That doesn't make any sense. But we use that in order to get the real value here. So let's do the original function value at the fixed point. So y is equal to the square f of 100, which is the square root of 100, which is 10. That's sort of our basis on the graph. That's where we're going to start on the y-axis. And then if we want y that is equal to f of 102, that's the square root of 102. That is what we are looking for. Then we know that this is approximately the y value at the fixed point for x, so f of 100 plus the differential. Now this piece is approximate, but everything I tell you afterwards is still the exact numbers. So this is 10 plus 0.1, which is 10.1. So the differential tells us that the square root of 102 is 10.1. Go ahead with your calculator and actually compute the square root of 102 and see how close it is. I think you'll be surprised. Well, you shouldn't be surprised because that's what teaching you for now. You should get 10.099 or something like that. I mean, that's just like almost on the money. Okay, go ahead with your partner and work. Example 6. All right, in example 6, we have the cube root of 120. We want to do that using differentials. So the function is the cube root of x, which is also written as x to the 1/3 power. The closest perfect cube to 120 is 125. Since that's ahead of 120, that makes delta x 120 minus 125, which is negative 5. So you can't have a negative on the delta x. It just means you're going to the left. Next, compute the derivative. So since f is x to the 1/3 power, bring the 1/3 down, times x, subtract 1 from the power, that's x to the negative 2/3. And then we have dy is equal to f prime of x times dx. So we're going to plug in the derivative into the differential. So it's 1/3 x to the negative 2/3 times dx. Use your fixed value of x, which is 125. The delta x is -5, and that's also dx. And then let's compute these numbers here. The cube root of 125 is 5. 5 squared is 25. And it had a negative exponent, so it's 1 over 25 times -5. And if you work that out, that's -1 over 15. And written as a decimal, that's -0.06666 forever, like that. So that gives us the approximation for the change in y. Now we will compute the actual change here. So we want f of 120, which is the cube root of 120. That is approximately f of 125, our fixed point, plus the differential in y. The cube root of 125 is 5, and the differential is negative, which is going to lower it. But notice that I didn't write a negative here. I just let the sign come out in the dy itself. And that's 4.9333, etc. All right, so a couple places where you got stuck, I think, was you need to be looking at the actual process that's going on with the numbers in order to work the problems. Since this one was a cube root, you need to use the cube root function, not the square root function.